Hello and welcome back. Today we cover sections 4.4 and 4.5, continuous growth. Project number 1 is due today. Project number 2 is assigned as of today. So take a look at the date next to this row, and whatever you see there, that's when project 1 is collected and project 2 is assigned. You'll find project 2 up on Moodle. You will turn in project 2 through project 1 through Moodle. Okay, let's go ahead and get started with class number 5. Last class, we saw the formula for compound interest. It was this one. What happens is we compound more and more often. So the problems we saw last class involved compounding monthly. But what if instead you decided you wanted to invest your money at a place that compounded more often than monthly? Maybe they give interest at the end of every week, or maybe they give interest at the end of every day, or maybe they give interest at the end of every hour. And you can keep playing this game until you get to a place where you're getting interest all the time. That's the goal, is to understand what's happening there. So in other words, what happens to this formula, this one right here, when n approaches infinity? N, remember, was the number of times you compound interest every year. As n gets bigger and bigger, what happens to that formula? It's going to become another formula, and that's one of the goals for today's class, is to find the formula that this turns into when n approaches infinity. So let's do that here. We're going to make a substitution. X is equal to n over r. It's not really clear why we're making that substitution, but just bear with me for a few minutes. We'll plug in that substitution in here. So first thing I want to do is take a look at this thing right here, r over n. Well, what does that have to do with x? We'll take a look. X, remember, is n over r. R over n is upside down from that. It's the reciprocal of that. So how do we write that down in terms of x? Well, it's 1 over x. That's how we make a reciprocal. And the other thing we can do is solve this thing here for n. If you multiply both sides by r, you see that n is equal to x times r. So let's substitute into this thing right here. So p times 1 plus, instead of r over n, well, we've seen right here that that's really the same as 1 over x. So I'm going to put 1 over x right there. And then upstairs, you can see the power is n times t, but instead of n, I'm going to put xr. So instead of n times t, it becomes xr times t. Okay, so far so good. So I'll call this a of t because that's what it's equal to. That's what it was at the top of the page right there. And let's just manipulate a little bit more, and then some good things will happen. So this is 1 plus 1 over x. There's an x times r times t up in the power. I'm going to write it like this: x, and then brackets, and then rt. And let's see whether or not we buy that that's the same. Well, you have right here something being raised to a power, which itself is being raised to another power. So maybe you've seen a formula for this before: x to the a, the whole thing to the b. What do you do to those powers? Well, hopefully you recognize that the formula tells you to multiply them. So the formula here tells us to multiply the powers together: x times rt. X times rt is exactly what we had before. So I haven't done anything illegal. These two expressions, this one and this one, are exactly the same. But now I want to take a look at the thing inside the brackets. Inside the brackets, just the 1 plus 1 over x to the x. Forget about the other stuff right now. I just want to look at that stuff in the bracket. It's written down here again. And we want to find the value of the limit as x approaches infinity. Now, why do I want to let x go to infinity? Well, take a look at what we were interested in up above. We saw before that we were interested in compounding more and more often. That is, sending n to infinity. Well, if we take a look at our definition here for x, r is just some number. It's the interest rate and it's fixed. But as n goes to infinity, if we send n to infinity, what happens to x? Well, you're taking n and you're dividing it by some fixed interest rate. So you're taking bigger and bigger values of n, dividing it by the same, say, 5% interest over and over again. What's going to happen is x is going to go to infinity as well. So sending n to infinity necessarily means sending x to infinity. And so that's why down here, we're interested in letting x go to infinity because it's equivalent to what we were interested in before, sending n to infinity. So we want to let x go to infinity of this yellow stuff. So it's actually really not clear at all what's happening when n goes to infinity, because when x goes to infinity, because on the one hand, I'm trying to do, so I'll just write it out. 1 over infinity. It's not good mathematically to write that, but we're just trying to get a sense of what's going on here. So I've got 1 plus 1 over something really big, and that's being raised to a power that is really big. Well, it's kind of strange. If for example, x is like 1,000,000, then I'm just looking at 1 over 1,000,000. And 1 over 1,000,000 is very close to what nice number? It's really close to 0. So basically that, you add 1 to 1 over 1,000,000, and it's pretty much just 1. So this is very close to 1, and 1,000,000 is a pretty small number compared to infinity. So, that number in the parentheses is basically 1. So we're just taking this thing, 1, and raising it to the infinity. And 1 to any power is 1, no? But on the other hand, it's never quite 1. And even if it's something like 1.000001, if you raise this to bigger and bigger powers, what happens to it? Well, every time you multiply by another 1.000001, the thing gets a little bit bigger. And so even though you're not adding much each time, you're adding something. And every time it gets bigger, and so this thing will actually head to infinity. And so we've got these two competing rules. We want, on the one hand, the thing wants to stay at 1. On the other hand, the thing wants to go to infinity. Who's going to win? Is it going to really get to 1? Is it going to get bigger and bigger and bigger? Is it going to balance someplace in the middle? That's what we're after here. So what we're going to do is calculate the limit by graphing. So on the calculator, type in y equals 1 plus 1 over x. With parentheses, 1 plus 1 over x. And then that's going to be raised to the x power. And then this is my way of telling you what I want the window to be. So let's make sure we know what this means. 0, 20, that's the x interval. So we just type in here, 0, enter, 20, enter. And then the y interval is the second one, this 0 to 3. And hit graph, and let's see what happens. So we're interested in finding the limit as x goes to infinity. As x gets really big, we saw these kind of two conflicting rules that were happening here. What's happening? Is it going to 1? Well, 1 is down here, so it doesn't appear that this function is getting close to 1. Is it going up to infinity? Well, it's going up, but the top of this window is 3. It sure doesn't feel like it's going to get to infinity, even if we let it run to the right forever and ever. It actually kind of looks like it's leveling off. So maybe we can use the trace command. You can use trace here, and you can just hold the right arrow and see what happens to the y values. And so you can see the y value right now is 2.627, and as you go to the right, it gets a little bit bigger. And at the end of this window, looks like we're somewhere around 2.65. Keep heading to the right, it will sneak the window a little bit further to the right. But I kind of want to jump the gun. I don't want to just sneak over by 1s and 2s. So why don't we, instead of going out to 20, let's go out to, say, 200. Keep this one here at 0, that's fine. And so now we'll graph. And at some point, I feel like it's just going to look like a horizontal line, even though it seems to be growing all the time. There's just not enough pixels to illustrate how tiny the growth is out here. But we can now trace, and you can just hit the right arrow over and over again. A little shortcut here. Once you've hit the trace button, you can actually tell it, I want x equal to 180. You can just type 180 right in here, and it will zip the cursor out to there. So now we're at 2.71. 2.710. Okay, let's jump all the way to the end of this window at 200. 2.711. Okay, let's play with this game one more time. Let's go out to 20,000. And it's basically just going to look like a horizontal line, even though it feels like it's still growing by tiny, tiny amounts. And then we can do trace, and then we can type in 5,000. And that's over here. We can do 15,000. We're up at 2.71819. 20,000 is the biggest one that I can do on this window. 2.71821. So it sure feels like we are honing in on some number, 2.718, and then I'm not sure what's going on next, but if I kept playing this game, I would get, it feels like closer and closer to some distinct number. It doesn't look like a nice number to me. It's not like it's 3 or 2, but somewhere around 2.718 feels like is a number. Number 3, we denote the special limit we found above with the letter E. So let's actually use the good limit notation that we saw last class. Limit as x goes to infinity. Now typically we would just put the y over here, but I'm not going to do that. I'm going to write the formula, which is an alternative to writing the y. 1 plus 1 over x to the x. And it sure looked like this was something around 2.718, and then I don't know what the next few digits are. So in number 3, it says we use E to denote this number. It's apparently an important enough number that it deserves a letter. And that's not so unusual. Can you think of another instance in math where there's a very important number and it has its own letter associated with it? So one common number that you guys know by its letter is pi. Pi is a Greek letter, but you know it as the number 3.14. And some of you maybe are thinking of I, which is the imaginary number, and that's another place where there's a number that's so important it needs a letter. So here's another number that's so important it needs a letter. So we use E to denote this number, 2.718 and change. It is this limit, it is that, and it goes beyond that, but 2.718 is our approximation at this moment. Okay, so let's go way back to where we were. This thing right here, as x went to infinity, the thing on the inside of the brackets, that highlighted yellow stuff, became E. So inside of the brackets, I'll just leave it blank for a second, put the P in the front, the R and the T up above, but all that yellow stuff is the same as this yellow stuff, and we've decided that the limit of that yellow stuff when x goes to infinity is about 2.718 and change, and we're going to call that the number E. So P e to the RT is what this formula at the top of the page becomes, right here. That becomes PE to the RT when we compound continuously all the time. That is to say, when n goes to infinity. So number 4, the formula for continuous compounding, meaning compounding all the time, is therefore A of t equals PE to the RT. Some people memorize that as PERT, like the shampoo. In this equation, R is called the continuous growth rate. That means you are getting interest more often than monthly, more often than daily, more often than hourly, more often than once every second. Continuous interest. Every instant of the day, you are earning a little tiny fraction of a percent of interest. Number 5. Suppose an account starts with $1,000 and compounds at 12% annual interest compounded continuously. Find a formula for the balance after t years. PE to the RT is our formula. The only time we get to use that formula is when you see the word continuously, compounded continuously. Use PERT. Okay, P is 1,000. E is just E. You don't replace it with anything. It's a number. It's about 2.718. R is 0.12, 12%. T is time. That's it. That's our formula. B, what's the continuous rate? Okay, the continuous rate, well, according to our definition, the continuous rate is R. So R is 0.12. So continuous rate is just R in the formula, PE to the RT. So the answer in this case is 0.12 or 12%. The effective rate we got to do work for, because to say that we're getting 12% interest is kind of misleading. To say 12% makes it sound like you're just getting 12% annual interest once at the end of the year. But we're getting 12% interest continuously, a little bit of interest at every moment of the year. So we want the effective rate. Okay, so how about we play this game? We're going to invest $1 for 1 year, and that's our standard way of finding out what the effective interest rate is. We did this before a couple of classes ago, actually. So $1 for 1 year. The final amount of money after 1 year is $1 is the principal, e to the 12% interest times 1 year. Okay, let's type this into the calculator. We should have $1 and then some change. We'll get some interest on our dollar investment. So okay, the E button. There's two ways to do this on the calculator. There's an E right there in yellow on the division sign. So you can do second E, and then you can do this power. And then we got to put parentheses here. I mean, you could just put 0.12, but I'll put all the details here. It's 0.12 times 1. So this is our answer. Better than that, I don't ever want to see you do that because E is almost all the time followed by some power, so often that it's got its own button. It's right here, e to the x. So instead of using this E button, much more useful is this e to the x button. So we do 1 second e to the x button. That 1 button right there eliminates the need to do the power, and it also eliminates the need to type the parentheses. And then we can type in 0.112, 0.12 times 1. We'll get the same answer, of course, but I just want to share with you that's the better way to do it. So 1.1275. So you have your dollar, but you also have an additional 12 cents and another 75 hundredths of a cent. So that extra stuff is the interest rate, the effective rate. So the APY is this 1.1275, subtract off the dollar that you had, and we get 0.1275 or 12.75%. So I'll write down a formula. I don't think it's typed up here in the notes formally, but I'll write it just in case you want it. But if you don't know the right formula to answer one of these questions, to find the effective rate, just invest $1 for a year. And hopefully the answer will be staring you in the face. If I tell you you have $1, $12.75, that $12.75 is the interest. And it's also the interest rate because you invested $1 for a year. So I guess I can say over here something like the APY, this is for continuous compounding. What is it? You take your E, you raise it to the R, and you subtract 1. See if that's reasonable. It's exactly what we did here. E to the 0.12. You don't have to write the 1 and you don't have to write the 1, but they were there. And then subtract 1. Subtract 1 is exactly what we did at the end. So that's how you find the continuous APY, where R is the continuous rate. So I'm not a fan of just having all these formulas and using them. I'd much prefer to think about things, and it's pretty easy for me to remember, oh, okay, just invest $1 for a year, and then look at the answer. Okay, part D, how much money will be in the account in 10 years? We'll just go up to our blue formula at the top of this screen, 1,000 e to the 0.12. So A of, so T goes in here, so it's 10, 1,000 e to the 0.12 times 10. We can type this into the calculator. 1,000. And then remember, we're going to use this one over here on the left, second e to the x, 0.12 times 10. So about 3,320.12. Part E, how long will it take for the balance in the account to grow to $5,000? So same, we're still using this formula at the top of the page in blue, but in this case, I want 5,000 at the end of the game, so that will be by itself on the one side of the equation, 1,000 e to the 0.12t. Trying to solve for t. Again, we don't have the tools yet officially in this class to solve an equation where the variable is in the power. That's coming very soon. If you have experience with logs, and in particular natural logs, then I'd encourage you to try solving this one on your own using that. But we are going to instead just graph both sides of the equation and intersect. This would be a good time to pause the video and see if you can find a good window. Think about the window, don't just randomly trial and error around. Think about the window and see if you can find the solution to these two. And come back when you're ready. Okay, so if you found the solution, good for you. Let's see if we can come up with a window here. So I know that we're waiting for the money to grow to $5,000 after 10 years. So you want to use the information you already have. After 10 years, you were up at 3,000, starting at 1,000 to get to 3,000. So it seems like probably within another 10 years, we should certainly be past this number right here. So I'll just go to 20. That happens to be what's already here. Well, it's not there. 20 is there. And then the y values, so the y values are what you typed in. They better be up at least at 5,000, otherwise you're not going to see anything. So 0 to, I don't know, let's say 10,000. We can go by thousands for the hash marks. So this will give me my 5,000 right in the middle of my window. There's something nice about that. And then we're just hoping to see some exponential growth thing. And if it intersects on the window, then we win. This was 0 to 20, so it looks like the answer is something around, I don't know, 12-ish. So let's do second calc and then 5, enter, enter, enter. And the point of intersection here, 13.4 years. And we'll have 5,000 in the account at that point. Okay, when you're ready, we go to the next page. Number 6, this idea of continuous compounding doesn't apply only to interest. If anything grows at a continuous rate of k, then the growth factor is e to the k, and the formula for the amount of stuff at time t is a e to the kt, which is supposed to remind you an awful lot of p e to the rt. It's just different letters. R was the interest rate, k is the growth rate. Let's take a look at this example. In 2004, the gross world product was 54.7 trillion, and it increases at a continuous rate of 3.8% per year. What's the formula for the world product in trillions in terms of years since 2004? What's the effective annual growth rate? Okay, so we'll start with our AE to the KT. Okay, it used to be P for principal. A is the same A from A times B to the T. A is the initial amount. And if initial means years since 2004, then we have a gift right there. In 2004, the initial amount was 54.7 trillion. That's A. So I will write 54.7. We'll assume everything here is in trillions. E to the, we don't know K yet. Oh, we do know K, it's given. The continuous rate of 3.8% per year, that right there is K. I know to use this PERT formula, or AE to the KT, because it says continuous. You see that word, you are using PERT or this equivalent business with A and K. So E to the 0.038, remember R, or the interest rate is always up there as a decimal. And that's our formula. So what does it say here? What's the formula for world product? We've got it, it's right there. And next part, what's the effective annual growth rate? So we'll use the formula that we wrote down on the previous page. You're welcome to, again, invest $1 and see what it grows to in a year. I know it's people instead of dollars, but it's the same idea. So you could just do $1 growing at 0.038 for 1 year, and then just subtract 1 from that. We'll go ahead and write down the formula from the previous page. It just said it's e to the r subtract 1. E to the 0.038 subtract 1. We'll get a decimal. Before we type it, you should pause the video and decide whether you think that the final answer to this problem is going to be more or less than 3.8%. Okay, make sure you close the parentheses when you use that button. It puts parentheses in. Subtract 1. Before we hit enter, we should hopefully have made a guess. 3.8% is the nominal rate. It's the named rate. But if this is growing continuously, then it's going to grow effectively faster than 3.8. So we're expecting a number bigger than 3.8%. So 3.87 seems reasonable to me. So that right there is the effective annual growth rate, APY, effective annual growth rate. 7. There are actually two different formulas for a continuous exponential function. A of t equals ae to the kt, the one we just used, and a of t equals a times b to the t, that's the one we've used in the last few classes. What can we tell from reading either form? All right, in either form, a is the initial amount. Money, population, doesn't matter. A is always what you start with. The k just has a name. It is the continuous growth rate. In our last example, it was 3.8%, not 3.87, but 3.8% is the continuous growth rate. That's just the definition of continuous growth rate. The b, on the other hand, is 1 plus r, where r is the annual growth rate. This is not continuous compounding. This is just the old traditional once a year give me interest or once a year give me new people in our population problem. So, so that's what the two different things tell you. If you have the b, for example, if we just made up a of t equals 3 times 1.07 to the t, then you can just look at that right away and know that the r is 0.07. 7% is the annual growth rate, not continuous, but just once a year, straight up 7% annual interest. Okay, how would we convert from the former to the latter? All right, so the former is the first one, latter is the second one. So converting from e to the kt over here to this b to the t. Well, I think we actually did it up above. We might not have realized that we did it up above. But when we have this 3.873, I think what we're saying is that the, let's write it here, the formula that we had in purple in the top left here, this 54.7e to the 0.038t, is really the same as 54.7 times 1 plus this r, 0.03873, raised to the t. And you can graph both of those functions on your calculator if you wish and convince yourself that one is landing right on top of the other. But those two functions are the same. So we'll highlight. This thing right here is just another way to write this formula right over here. So on the one hand, it's 3.8% continuous interest rate. That's easy to read from that formula. On the other hand, it's a 3.873 effective annual growth rate. That's what we can read from that formula. So how do you convert from the one to the other? Well, you just set e to the r equal to b. Maybe that's not the best way to say it. Let b equal e to the r, and you're done. Something's fishy. I need a +1 in here. Yeah, b is one more than whatever. No, b is just e to the r. So that's it. That's how we go from the former to the latter. Going the other direction, though, means finding r in this equation. And again, we need logs. We don't have them yet, but we will soon enough. Okay, the activity is here. So you're going to want to spend some significant time working through the activity. If you go through far enough, you'll eventually find an answer key, learning objectives in the usual place, and there is a video to the activity. It's got the standard name, 108 class 5 activity. no spaces.